All right, so hello everyone, welcome back to the course. And are there people here? Yes, there's people here. Okay, all right, great. So let's see, where were we? So we were deep into code generation, right, for assignment 5. And so today I want to finish code generation, and then I'll have some let's say advanced topics for the remaining lectures. I guess we have today and then 3 more lectures left in the course. Okay, so we were looking at code generation, and there were all these lectures about planning your memory layout, deciding on conventions, that sort of thing. And then on Monday, we talked about how to generate code for each kind of AST node. I have sort of 2 difficult AST nodes left. So I ended off over here with generating code for a method call, right? So if I have an AST node for a method call that has a receiver O, and again, the receiver could be some complicated expression. And in this case, I have 1 argument A. And again, that could be a complicated expression that needs to be evaluated. So, and then I started generating code to implement that method call. All right. And so I have some code that's going to evaluate that receiver expression. Then a null check that's required for by Java for a method call. And a code over here to evaluate the argument. And both the receiver and the argument are pushed onto the stack. And that's, of course, assuming that my convention for passing parameters is to put them on the stack. So, conventions. So parameters, well, or receiver and parameters. Receiver parameters on stack, and they are pushed from left to right. And I think I talked earlier about the varying conventions that for C, for example, typically they use an opposite convention where they push the arguments onto the stack from right to left. The thing that's important here is that any of these expressions, the O or the A or one of the other arguments, if there were multiple arguments, any of these expressions could have side effects. So in general, we always need to evaluate them in the order that they appear in the JUICE code, right? So O first, and then the first argument, and then the second argument, and so on. So if you were doing an opposite convention where you wanted the arguments on the stack from right to left, then you would still have to evaluate them from left to right so that the side effects happen in the right order. But then you would have to reverse them and push them onto the stack. Or maybe you push them onto the stack and then you write a little reversing loop that's going to reverse them, once they're already on the stack, or something like that to get that convention, right? Or you could detect that, maybe you have simple expressions that don't have side effects. So there's lots of ways to do it. I think for JUICE and Java, following a left to right convention is easier because that's the order in which you get the arguments. Okay, so we have the arguments evaluated and the receiver, and we have them pushed onto the stack. And now we need to figure out which method we're actually calling. And I talked a lot about this when I was talking about the object layout, right? We need to decide on the implementation of a particular method M based on the runtime type of that this O evaluates to, right? We don't know from the static type of O which method M to call, but we have to do this dynamic dispatch where if the type of O is fruit, but then the actual object we get is an apple, then an apple might have a different M method than an orange. Okay, so we have to look at this object that we have, and we pushed it onto the stack, and then we pushed the arguments on top of it. So what I'm going to do is pull that object back from the stack. So I kind of want to pop twice to get this object, but I don't actually want to pop the argument off the stack. So I'm going to kind of cheat and do a pop instruction that doesn't actually pop things. So I am going to take the stack pointer +4. So that's going to be, the stack pointer points to the top of the stack. So this argument that I pushed +4 will point to the second word from the top of the stack, which is the object that I'm calling. Okay, so this is going to be, okay, I want to put a comment here, but I don't have any more space. So I'm going to put the comment over here. I know that's weird. Address of O, right? Address of the receiver is going to go into register EAX. Okay. So, and obviously, if you had more than one argument, that 4 would change to reflect however many words you have pushed onto the stack. Okay. So now I have the address of this receiver object O in the stack. And then I'm going to assume the object layout that that we have, and I'm also going to assume that the static type of O is a class, not an interface. Okay, and so if the static type of O is a class, then I can find that method M at a constant offset in the class table for that object O, right? If the static type was an interface, then the method M, together with its type is a selector, and I would have to do a different piece of code to find a method with that specific selector on the runtime object, right? So I would use my selector index table. So this stuff, this code would change if I had an interface. But I'm sort of assuming the common case where the static type of O is a class. So I'm going to go from the object to find the class. And with the convention that I had earlier, I have a pointer to the class at the very beginning of the object, in the first word of the object. So I can say EAX +0 or just EAX. I mean, the assembler is going to generate the same machine language code for both, hopefully. But anyway, I'm just dereferencing EAX, right? I'm just reading that first word of the object, and that is going to give me the class information of the runtime type of that object. Okay, and sort of, you can follow the same pattern in other places where you need information about the runtime type of an object. Like there was some discussion on Piazza this morning about type tests. Oh wait, that might have been a private Piazza message. So anyway, but when you're implementing casts and instance of expressions and array assignments anywhere where you need to do type tests, this is how you get the type information, the runtime type of an object. Right? So So this is going to be the class info of O. Okay, and so now I have the address of the class info of O in register EAX, and then since the static type is a class, for each method in that class, I have a compile time constant offset at which I find it in the class information. So here I'm going to do another move. And yeah, they're all move instructions, but I'm doing different things. So here I'm going to do EAX plus the offset of method M. Okay. So that offset, that's going to be a compile time constant. In my compiler, I'm going to map each method to the word in the class table where its address can be found. And so here I'm going to put that constant there. And so this gives me the address of the implementation of the method M of the actual runtime object that I have, right? So if it's an apple, this is going to be the address of the M method on apples. All right, and so now I have the address of the method. I've pushed the arguments on the stack, so everything is ready to go. And I can just do the call, and I'll do call EAX, right? And so this will be an indirect call. It'll call whatever address I have in register EAX, right? As opposed to a call to a fixed memory address, right? If I was calling a static method, I would have a label that would be a fixed memory address for that static method, right? Because I would know at compile time exactly which static method I'm calling. Okay, and so if there's questions, do ask questions. And while you ask questions, I'm going to add a bit more here. So I call the method, it does its thing and it returns. And then, as we discussed earlier, we just pushed two things onto the stack, so we should pop them off, right? I suppose, yeah, okay, so we should pop them off. So I'm going to add, I could do 2 pop instructions, or if I want to do the 2 pops in a single instruction, I can just add 8 to the stack pointer. That will pop 2 words off the stack and throw them away. If I wanted to preserve the arguments for some reason, I could use a pop instruction, right? That would pop them off the stack and move them into a register for me. Okay, so so that's sort of the general code for method calls. But yeah, I mean, you need to modify this code for a static method, right? So for a static method, you would have a fixed address that you're calling here. You don't need to do the runtime type lookup. So you just push the arguments on. You wouldn't have a receiver either, but just the arguments, and then a call to a label, and then you'd pop the arguments off as well. On the other hand, if you had an interface method, it would be more complicated than this, because instead of this code for looking up the method, you would be looking up a column of the selector index table, and then you would be looking at an offset in that selector index table. All right. So in terms of how the code would actually look, depending on how you lay out your memory, if you kind of did it the way that I hinted at and that I have in mind, I think you would have 1 extra move instruction here to go from the class information to the column of the selector index table. And then the offset, of course, would be a different kind of offset rather than being the offset of that particular method within the static class of O. It would be the global offset of that selector in the selector index table. All right. So I don't know. I mean, it feels like there's a lot here, and that I've said a lot. So I'm kind of worried that there's no questions. So if there's questions, do ask them. The next kind of AST node that I want to go to is an object allocation or an object creation node. So for a new expression, and it's going to have, some things in common with method calls and also some different things. So, all right, questions? No? Okay. Well, I mean, you'll have the whole lecture to ask questions if you think of them later. Okay, so let's look at object allocation nodes. All right. So this is something of the form, well, I have a new, okay, so I have a new A. All right, so I'm creating a new object of class A. Whoops. All right, so I'm creating a new object of class A. The constructor of A, takes some number of parameters, maybe 0, maybe 1, maybe more. For the sake of example, let's just say 1 parameter. Okay, and so partly it's like a method call in that I'm going to call the constructor. But before that, I mean, in the method call, I had this receiver object. And in the new, I'm actually creating that receiver object, right, before I call its constructor. All right. So the way so I need to allocate memory for this object. And so the way I'm going to allocate memory is I'm going to call the underscore malloc function that is given to you in the runtime.s. So this is a short piece of code that asks the operating system to give me some number of bytes of memory, and in a real implementation you would have some sort of a heap data structure to keep track of this memory. Probably for Java and for Juice, you would have a garbage collector that would keep track of when areas of memory become unreachable. And I mean, the interaction between the compiler and the garbage collector is a pretty tricky topic. So I don't want you to have to write a garbage collector in this course. I guess I have had, in some cases, some people taking the grad version, they tried to, as an extra project, they tried to write a garbage collector. So it does, I do sometimes have enthusiastic groups that want to write a garbage collector, but it's a lot more tricky than in practice than it appears in theory, right? In theory, it's like, yeah, okay, I could write a garbage collector, and then it pulls in a lot of details that are not obvious at first, and it makes debugging really painful. So, okay, so we're not doing a garbage collector, unless you really want to. So all we're going to do is allocate space for this object, and we're going to never free it, and we're just going to hope that our Juice programs are small enough that we won't run out of memory. Okay. So all right. So we call malloc, and malloc calls the operating system, give us some memory. But if you look at the comments in runtime.s, they say that malloc needs the number of bytes that you want to allocate in register EAX, right? So before I call malloc, I'm going to move into EAX. The size of an object of class A. Okay, and I know what class I'm allocating, so the compiler has to keep track of how much information there is in an object of class A, how many fields class A has, and so on, to figure out how many bytes we need. So just note that this is in bytes. And then malloc is going to give us the address of that many bytes in register EAX. Okay, so now EAX is going to be the address of the new object, right? The address of the receiver of the constructor, right? So I'm going to create a new receiver, and then I want to call its constructor on it. So like here where I evaluated whatever I had in EAX, that's what I have in EAX over here. Okay, but before I call the constructor, I should initialize this new space. Okay, so what does that mean? Well, I need to initialize that first word right here of that object to be the class information. So the address of the class information, in this case of the class A. All right, so I'm going to do that. So I'm going to dereference EAX, right? I could write EAX plus 0, so the first word of the object with the class info for class A. And this class info for class A, this is a compile time constant data structure that your compiler can generate and create a label for it, right? That has the addresses of the various methods of M. Sorry, the various methods of A. So here, this is just going to be a label, and it's going to get assembled to a constant address. Okay, so we're just loading that address into the first word of my object. All right, so again, questions, ask them in the chat. Okay, and I said we need to initialize A. So you were probably thinking we should initialize the fields of A to their initial values, right? Like if I declare a field in class A, like int x equals 42, should we put the 42 in there? And I'm going to not do that here. And instead, I'm going to do that initialization inside the constructor itself. Okay, so malloc, the space that malloc gives us is already zeroed out. So all the bytes are zeros, which is what the initial value should be before you actually initialize a field. But I'm going to implement the field initializers inside the constructor itself. And the reason is that the field initializers, they can be something simple like 42, but they could actually be more complicated things. So in particular, you could do a method call inside a field initializer, right? So you could say, int x equals, this dot m brackets, and the field initializer would need to call method m and do whatever method m does, and then whatever it returns, that would be what gets initialized to the field. And So in order to support complicated expressions like that, it's easier to support them in the constructor of A, because to call this dot m, you need to have a value for this, right? And you need to be able to evaluate the current receiver, and you don't want the this of the code that contains the new instruction, because that could be in a different class. You really want to be in the context of that new object that you've created. Okay, so in that sense, it's easier to implement the field initializers by sort of translating them into code that is going to go into this constructor. And I just want to mention that Java and Java-C, right? So normally when you compile Java code, you don't compile it to machine language directly. You use Java-C to compile it to Java bytecode, and then you use a second JIT compiler at runtime to compile the bytecode to machine language. And in the case of Java-C, what happens is in the bytecode, the field initializers are gone, and they are actually translated into bytecode that's part of the constructor, right? So I guess the point is that Java-C does it this way as well, even though it's not generating machine language, even though it's only generating Java bytecode. Okay, so all that to say that we're not initializing the fields here. So what are we doing? Well, we're basically going to do the rest of the method call, right? We've created the object, we've initialized it as much as we're going to initialize it, and now we just need a call to a constructor. And a constructor is similar to a static method in that the constructor for class A is at a fixed offset, at a fixed address, a fixed label. So we don't need to do this dynamic dispatch to find the constructor. Okay, but we do need to pass parameters to the constructor. And just like here, the first parameter is the receiver. So we're going to push the receiver. Right, so I'm going to push EAX onto the stack. And so this is the receiver, the address of the object that we've just created, and also sort of the 0th parameter to the constructor. And then I'm going to evaluate any other arguments. So I'm going to say code of A, right, to evaluate that, in this case, the one argument A, and evaluate, get its value in EAX, and I'm going to push that onto the stack as well. Push EAX. Okay. All right. Okay, so I've got the arguments, the receiver and the arguments on the stack. Again, left to right, right? Just like our convention before. And now I am going to have a call, and it's just going to be a call to the constructor of A. Okay, and that's a fixed label. So the compiler just generates that label, and it's going to be a call to a fixed address at runtime. All right, and then I'm almost done, except, just like here, I need to pop the arguments. I should put a comment here for that. Pop arguments. All right. And in this case, I'm going to do it a little bit differently. So I'm going to add, only 4 to ESP, to the stack pointer, and then I'm going to pop EAX, and I'll get my red marker to connect these up. So the idea is if I match up the pushes and pops, so okay, pop args. So okay, so I again I want to pop the arguments off the stack, but in this case, that receiver, right? That's the object that I just created. I want to keep the address of that new object in register EAX, right? Because this is my new expression, and the new expression should evaluate to the address of the new object that it has created, right? So, here I wanted to throw away all the arguments. I don't need them anymore. Whereas here, what I want to be left with in EAX is the address of the new object, which happened to be on the stack as the receiver. Okay, so any questions here about how I'm calling the constructor? Okay. And again, I'm hoping that you can extrapolate from these two code examples to also deal with calling static methods and calling interface methods, right? They're going to be slight tweaks of these in the sense that for a static method, it's going to be like this in that you have a label that you're calling. You won't have the object creation, of course, but you'll have a constant label that you're calling. Okay, so, once again, questions do ask. I do want to say one more thing about constructors. Right, so, and I know I've already talked about constructors a bit. The implementation of constructor. It should do three things. And, two of them are maybe sort of obvious-ish. The second thing it should do is execute the field initializers. Okay, I'll just erase this here. Right, so, for example, if you, in your class, if you have, some expression like this, then, as the initializer in the declaration of X, you want to move that that expression as if it happened inside the constructor, right? So inside the constructor, you want effectively an assignment statement that is going to assign to the field X of this. So you want like this dot X, gets assigned M2, right? And sort of generate code for this kind of an assignment inside the constructor, as if somebody had written the juice code in the constructor itself, rather than as the initializer expression. And that's the easiest way to handle, all the various weird and complicated things that people could do inside initializer expressions. At least in Java, they're somewhat limited in that they can only be expressions and not statements. But in some other languages, the initializers could be even more general than that. So the easiest way is to just embed them inside your constructor. So that's step number 2. So what about steps 1 and 3? Well, okay. So step 3 is kind of obvious in or maybe obvious in hindsight. So in the machine language implementation of my constructor, I should include the actual, so the actual juice constructor body, right? So if somebody writes in their juice program a constructor that has some code in it, then you want to compile that code and put it in the generated constructor after the field initializers, right? So the way that Java works is that the field initializers run first, and then the body of the constructor runs afterwards. Okay, and then I'm left with number one. So what do you do before you initialize the fields? And so the one other thing to do is to call the superclass constructor. Okay. So unless you're already at Java Lang Object, and so this is I guess this is a Java requirement that before a constructor starts running, it needs to call a constructor of the superclass. Okay, and so that way, any fields that are that are declared in the superclass of the current class are going to get initialized first, right, before the current constructor even gets to run. And sort of Java requires that, and so this will ensure that. And this is another reason why you want to implement field initialization. Whoops, field initialization. Inside the constructor, because of course M and M2 could have side effects. And again, the Java rules are you initialize the fields of superclasses first, so any side effects that they might have would run first. And if you actually implement a call to a superclass constructor here, then this will do exactly what Java requires. And in Java, things are more explicit. So in Java, at the beginning of a constructor, you can use the super keyword to call a specific constructor, right, with a specific list of argument types. So you write your constructor of your subclass, and as the first line, you say, super, and you put some arguments, and that will translate to the constructor starting with a call of that specific constructor of the superclass, right? The constructor with the signature that matches the arguments that you're passing to super. In Juice, things are simpler in that there's no super calls, so you can't explicitly say that. And so there, Java says, if your constructor doesn't start with super, then you're still going to call a superclass constructor, but you're going to call the superclass constructor that takes 0 arguments, right? The constructor with no arguments. In Juice, you can't sort of override that default behavior because there's no super calls. So in Juice, you always call the 0 argument superclass constructor. So I guess I can fill that in here. Call the 0 argument superclass constructor. And somewhere in, I think, assignment 2, when we were checking the class hierarchy, one of the checks was that every class has one of these 0 argument constructors. So we're good there, right? We always have one to call. There could be other constructors, but you would always call this particular one here. Okay, so constructors, they kind of seem obvious when you're using Java, right? It's like, everything just kind of works, and it doesn't seem like there's much complexity there. But then when you go to implement it, actually generate code for a constructor, it doesn't seem that obvious, and things get tricky, especially with initializers and potential side effects of initializers and order of initializers, and so on. But so just if you follow this recipe, then you'll get the right behavior. All right, so this is what to do for constructors. Okay, so that brings me to the end. I'm going to stand over here. So that brings me to the end of this sort of section on, how do we generate code for each kind of AST node in the program, right? Obviously, I haven't covered all the AST nodes, but I think I've covered the main ones, and the the remaining ones are sort of variations on these themes. So I know I've been asking for questions, but are there questions now about code generation? Okay, so there's I guess one thing, general thing I want to say about code generation, and so I know you're all of your groups are working hard on assignment 5, and that's great. We have I guess today's Wednesday, right? So you have exactly 2 weeks from today to finish that. So that should be enough time. Hopefully you're not just getting started now, right? Hopefully you've started at least planning your memory layout by now. But we have 2 more weeks for assignment 5. And the one reminder is that the marmoset tests for all the assignments, but specifically for assignment 5, they test the various individual features of JUICE, but there's no sort of larger real-world tests. So I want to remind you that the secret tests test your compiler, and they test whether your compiler can actually compile real stuff, right? And as opposed to a small little test that each tests a single feature. I don't want you to be worried about what exactly real stuff is. So they are not testing corner cases, right? So they're not tests that are designed to trip you up. They're also not testing. They're not huge programs. Someone asked in Piazza how big they were, and I think the largest is around 300 lines of code. So they're programs that actually some former students wrote, in response to a question that was something like, okay, so you're going to spend a whole term writing a JUICE compiler. What program would you like it to compile, right? Write yourself a little JUICE program that does something, somehow useful or interesting or fun or not just a boring test case, but just does something, and and it's sort of the code that people naturally wrote to solve whatever problem. So in terms of your own testing, I mean, I'd encourage you to do that as well, right? Use your imagination to, if you had to write a program that does something fun, what program would you write? And, write yourself some little JUICE programs that exercise your compiler beyond just the marmoset tests. So you want to make sure that you can handle programs in general. And then one sort of specific thing related to the secret tests. So in the assignment 5 tests, there's a whole bunch of test cases, and all but one of the test cases, they don't produce any output. They just return, in this case, it's always the value 123, right? 123. But there's one test in assignment 5 that's like the hello world test, right? It just has a system out print line, hello world, and when it runs, it's supposed to print hello world to the standard output. So, I mean, that's a very small, simple test, but it's very important. You should make sure that you pass this test. You should make sure that you can print hello world, because the secret tests, I mean, they're all programs that do something useful. They produce some output, and so they do actually print something to the standard output. They don't just all return 123. So, if you can't print hello world, then you're not going to pass any of the secret tests. So it's kind of focus on, and you also need to implement all the various AST nodes and statements and expressions and all that. But make sure that that test that does the printing and prints hello world, that works, so that you can generate output, because all the secret tests do generate output. The other thing I wanted to say is all of the secret tests are valid JUICE programs. So in that sense, I suppose you could say that they don't test assignments 1 to 4. That's not actually true, because they do test them indirectly, in that any JUICE program in assignments 1 to 4, the compiler is building up data structures, right? It's resolving names, doing type checking, figuring out types for things, and all of that is stuff that you need to compile the code. So they are testing that sort of indirectly, but I always have students worrying about, are there some corner cases of invalid JUICE programs, right? The kinds of things that were tested very carefully in the assignments 1 to 4 tests. Do I have some sneaky cases of invalid JUICE programs that your compiler needs to recheck? And the answer is no. I don't have sneaky things like that in the secret tests. Okay, so they're supposed to be realistic programs, not sneaky, valid JUICE programs, not things where you have to detect an error. Okay, and now I've got some questions. So I think that's what I wanted to say about secret tests. Okay, but I'll repeat it one more time. Warning: just because you pass the A5 Marmoset tests doesn't guarantee that you're going to pass the secret tests, and you should do more testing after you've passed all the Marmoset tests. And this is sort of based on past years, past experience, right? I sometimes get groups that are surprised that, oh no, we passed all the Marmoset tests, and yet we didn't do well on the secret tests. So okay. So okay, so I've got a question about the constructor. Okay, good. So let's look at the constructor. Do you execute field initializers in step 2, even if fields are assigned in the constructor body? So yes. So so the way that the Java spec specifies things is that sort of initially all the fields have 0 values or null values if they're references, so that for example, if I were to access a field inside a field initializer before it had been initialized, and there were checks in assignment 3 that prevent that, but they don't always prevent it, right? So for example, this method M could read field X before it gets initialized. So there, in that case, the Java spec requires them to be that field to have the value 0 before the initializer runs. And here we have that, right? Because they're zeroed out by malloc, so they start out as 0. And then if you read a field in the constructor, before you write to it in the constructor, then it's supposed to get the value that the field initializer gave to it. So even if you are writing to the field in the constructor, you still want to execute the field initializer before you run the body of the constructor. Okay, and the other possible case, maybe the constructor writes to the field, but conditionally, like inside an if block. So again, in that case, you want the original field initializer to run first. So the rule is you always run the field initializer and then you run the constructor body. And if the constructor body overwrites that original value, that's fine, but you always run the field initializer first. Okay, so Brian, hopefully that answers your question. And Felix, all right, so is there a possibility of having the secret tests on Marmoset so we'd be able to see how many we would pass? I see. So I think the question is, can I tell you ahead of time, like, hey, you're passing 50% of the secret tests, you better, fix your compiler a bit, right, before the deadline. So I generally don't do that. So the secret tests are meant to be, a sample of a bunch of test cases that measure, one, sort of how robust your compiler is. Is it generally correct, or is it sort of designed to the tests? And secondly, how thoroughly you have tested the compiler, right? So in that sense, I always run the secret tests at the very end, and you get what you get. That said, when I run the secret tests, I always go through manually, and I've got a big class this year, so that's going to be patient when I'm going through the secret tests. But I run the secret tests and say half of them pass. I always go through manually to see the ones that fail, and I try to figure out why they fail, right? And in some cases, in most cases, they fail because they're supposed to fail, like because there's some feature that's not implemented correctly, or whatever. But sometimes it happens that maybe all the tests fail for some really stupid tiny bug, and in those cases I do kind of a case by case kind of thing. It's a slippery slope because it gets subjective there. But if it's a really tiny bug that's making you fail, all of the secret tests, I often will contact the group and say, hey, you have this really trivial thing, and if you fix that, I'll give you, not necessarily all the marks of those secret tests, but a big chunk of the marks of those secret tests. Basically, depending on how tiny the bug is and how many tests it affects, right? So I do go through and check manually that the score you get on the secret tests is fair compared to sort of how should I phrase it, right? So how many you're failing and how badly you're failing them, right? So I try to make that be fair in that sense. But I don't run the secret tests early to tell you how much more of your own testing you need to do. So I think my advice is, first of all, finish your compiler, right? And I know you have a lot of work to do to get it done. So even getting the marmoset test to pass, right, is a lot of work. So and then once you've finished it, write yourself some JUICE programs. Try it with some programs, test it, and then don't worry too much, right? And eventually the deadline comes, and then I'll run it on the secret tests, and we'll see how it did. But typically, the secret test results sort of correlate fairly well with with two things. One is what groups tell me in their final report about how thoroughly they tested things, right? So, the groups that did decent testing tend to do really well on the secret tests. And it's uncommon for a group to have lots of their own tests and do badly on the secret tests. And then the other thing that they reflect is sort of the general quality of the design of the compiler. So, for sort of compilers that tend to not pass too many of the secret tests are ones that have a lot of ad hoc things, especially if sort of throughout the course, if you kind of did things that were directly in response to the marmoset tests, as opposed to having a general design that should work in general for JUICE programs, right? So they kind of reflect that general design of the compiler. Judging from the reports that I've been reading, I think most groups have very good designs and general designs, right? And they're not sort of special cased to the specific marmoset tests. So I'm optimistic that lots of groups will do well on the secret tests. Okay, that was a long answer, or two long answers to two short questions. All right, are there other questions or other stuff? Okay, so I want to move away from code generation, and I have a few more topics that are advanced topics in terms of okay, so now you have a JUICE compiler that works, and how could you make your compiler better, right? What could we do beyond just getting JUICE code to compile it and run? How could we generate better code? So these are topics that are not required for the project and not required for the assignments. So that's why I've saved them to the last few lectures, right? Because I know you're all working away on the project and trying to. So I wanted to get the lectures that were specifically needed from the project for the project out of the way first. But sort of the general theme is compiler optimizations. So this would be more of the topic of a graduate course that's specifically on optimizing compilers. But one topic that I kind of skipped over in the middle, right, was static analysis. And I want to talk about static analysis first, because if you are doing optimizations, sort of the first thing you want to do is do static analyses to predict how your program is going to behave when it runs, and then you can transform the program to based on the results of those analyses. And so we got a little taste of a static analysis in assignment 4 with the reachability analysis, and I want to expand on that and look at some other analyses and sort of generalize that to static analyses in general. Okay, and I've got Sam has a question. How do we specify the entry point of the program? So the assignment 5 spec has or should have a paragraph that talks about that. But the idea is it's a method called test, and it's the method in the first class that's specified on the command line, right? So on the juice-C command line, you get a list of classes to compile that includes the standard library. So the very first class must have a test, a method called test, and that's the entry point of the program. So yeah, right. Or was your question about the entry point of the compiled code? Yeah, okay. So I think for the compiled code, that's also talked about in the assignment 5 spec. And if it's not clear there, ask on Piazza. Okay, so static analysis. Maybe I'll go over here. I mean, we did do the reachability analysis, right? So for just to refresh your memories a bit for the reachability analysis in assignment 4, we had these two sets for each statement, right? And the idea was, can statement S start executing, and can statement S finish executing, right? And the potential answers were no or maybe, or maybe or no. Okay, right. So we all remember that, right, from assignment 4. And so I want to go to a slightly more interesting analysis, and this is one that's required for Java, but not required for Juice. And so Java definite assignment right, so this is an analysis that ensures that before I read a local variable, I always initialize it first. Right? So initialize local variables before they're read. Okay, and again, this is a response to a common bug in C programs that people will assume that variables are initialized to 0 and they'll read them, but in C, local variables will have some random value, like whatever happened to be on the stack before the method was called. Right? So in Java, there's this static analysis that for local variables only, but that ensures that you never read a local variable unless somebody has written a value into it at first. Okay, and so the way we're going to set up this analysis is with in and out sets like before, but the sets are going to be more interesting now. So I'm going to have for each statement S. And actually, S can also be an expression E. So we're going to change things around. We're going to have these facts not only for statements, but also for expressions and sub-expressions. And then the values are going to be, no longer just maybe or no, but each value is going to be a set of definitely initialized variables, and I'm going to say before S executes, and then similarly, out of S or out of E is going to be the same thing after S. And I guess I should say S/E. All right. So things are more interesting now. Our values at each program point are no longer just maybe or no, but for each program point, or before and after each statement, and now each expression and sub-expression, I'm going to compute an entire set rather than just maybe or no. And it's going to be a set of definitely initialized variables, right? So these are variables where I know for sure that the variable has been assigned a value by this point. And there is kind of a maybe no or maybe yes flavor to it, right? In that if I know for sure that a variable has been initialized, then I can put it in the set. And if I'm unsure, right, if I think, well, it's probably initialized, but maybe not, then I just leave it out of the set, and that's going to be a correct answer, right, a conservative answer, but it's not going to be untrue, right? If I leave out a variable that actually is initialized at runtime. Okay, and so then if I've done this analysis, then when do I give an error? Well, so if I have an expression E that reads variable V, right? So if E is a read expression that reads variable V, then if V is not in of E, then I give a compile time error, right? So the analysis has to be able to prove that, by the time you read a variable, that it is in the inset of E, so it has been definitely initialized right before I try to read it. So this is how the analysis is going to work. And then, then I just have to implement the analysis sort of in the same style as the reachability analysis. I'm just going to go through the various kinds of statements that I might see in a Java program and write sets of equations for those statements. Right. So and there's only a handful that are relevant for this analysis. So I'm going to have one kind of statement that's going to be a block with a declaration. So if I declare a variable with some type tau, and I initialize it right away, and then I have one or more other statements in the block, then what kinds of equations should I write for this? Well, I'm now going to have equations that involve expressions, not only statements, right? For reachability, they only involve statements, but I need a value for the in value of E, the in value of S, and then the out value of the overall AST node as a whole, right? So this is sort of like the kinds of equations we had for the reachability analysis. A difference now is that these equations involve sets rather than values that are maybe or no. So for in of E, before E executes, what is definitely initialized? Well, it's just going to be in of L, right? So in of the block as a whole. What about in of S? So, when I start executing S, what is initialized? Well, sort of the way the execution works is I go into the block, I execute E, I get out of E, and then I go to S. So in that sense, I should have out of S. But after I finish executing E, I take its value and assign it to X, right? So here I know, so I'm going to do a union with a set containing X, right? Because, whoops, I said out of S, and I meant to say out of E. So whatever variables E initializes, right? So E is an expression, but it could have rights to other variables. So it will initialize them, and then those variables would show up in out of E. But after I execute E, I also initialize X, so X is going to be in the set here. Okay, and so that's going to be in of S, and then I need a value for out of L, and that's just going to be out of S. So whatever is initialized after I execute the body of the block is initialized after the block. Okay, so if there's questions, feel free to ask. But I can move on to a block that declares a variable without an initializer. So, here I declare variable X. I don't bother initializing it. So this would not be allowed in JUICE, right? The way that we make this safe in JUICE without having to do this analysis is by disallowing this kind of thing and requiring an initializer. But in Java, it's more flexible. So here I need an in of S and an out of L. Okay, and when I go into S, it's just in of L, right? So whatever variables were initialized when the block started, those are the variables that are initialized when I go into the body of the block. The declaration of the variable didn't initialize any variables, right? So nothing changes here. And out of L is just out of S. So in that sense, this kind of a block is really boring. And now, but what's interesting for a definite assignment analysis? Well, it's an interesting instruction is an assignment instruction, right? Or an assignment expression. So if I have an expression that assigns some value to variable X, this is where I want to tell my analysis that this assignment expression is going to definitely assign to X. All right. So how do we write equations for this? So I'm going to say in of E and out of L. Okay, so when I start evaluating the expression, nothing has changed yet. So in of E is just in of L. So whatever variables are initialized before I start doing the assignment, those are the variables that are initialized. But then out of L is going to be out of E, unioned with a set that has X in it. Okay. So this is sort of the key instruction that matters for the initialization analysis, right? So when I have an expression that writes a value to X, after that write, I'm going to know that X is initialized. And now I have one more, interesting, interesting kind of JUICE instruction, and that is for an if statement. And really, it's for any statement where there's a control flow change. So you could do this for loops as well. Okay, and so I need in of E and in of S1, in of S2, oops, yeah, S2. And out of L. Okay. All right, so in of E is just going to be in of L, so there's nothing new evaluated. And now for in of S1, I'm going to evaluate the expression. So if the expression, the condition, if the condition initializes some variables, then I want them to be initialized. So in of S1 is going to be out of the expression, and similarly for in of S2. Okay. But now, what about the out of the if statement? So what happens? So I'm going to go through S1, and that might initialize some variables, or depending on how the conditional turned out, I'm going to go to S2, and that might initialize some variables. But in terms of the compiler, in terms of the static analysis, I don't know which path I'm going to go down, right? So when these two paths come together, I need to somehow combine the two sets, right? So I have out of S1, and I have out of S2. Okay, and so depending on the specific static analysis that I'm doing, when two control flow paths come together, I need a way to combine two different values. I guess in the reachability analysis, we took the OR of two values that were no or maybe. In this case, I'm going to take the intersection. Okay, and so typically when you have an analysis where the flow values are sets, typically you merge them either with union or intersection, and which one you do depends on the specific analysis that you're doing. In this case, I'm trying to come up with a set of variables that are definitely initialized, and so if I don't know which path I came in on, I want the intersection, because I only want the ones that are definitely initialized on both of those paths that I might have taken to get in here. Yeah. Okay. All right. So so once again, sort of this combination operation depends on the type of data flow values. So if they're Booleans like no or maybe, then it's usually an or an and. If they're sets, then they're intersections or unions. But in more complicated analyses, you can have even more complicated kinds of values, and then this merge function would be some potentially complicated function. Okay, so I'm not going to do all the AST nodes. I've done sort of a few of the interesting ones for the definite assignment analysis, just to give us an idea of how a more general analysis. One thing that's still the case here is the equations are not recursive, so you can do a single pass through the program, and you can just solve the equations just by implementing them directly. So if I want to compute out of L, well, I'm going to compute out of S1 and out of S2 and intersect them. And, that's going to recurse into S1 and S2, but I'm never going to have a case where I'm going to come back to out of L. Most, more general static analyses are recursive. So these equations, you set them up in the same way, you get these systems of equations, but now the equations can be recursive. So out of L can depend, transitively going through multiple equations, it can depend on itself. So I want to talk about that on Monday of, okay, so, what are we going to do if there's infinite recursion in these equations, right? Because then we're not going to be able to implement them recursively. Okay, so we'll look at that on Monday, how to do static analysis in general when your equations can be recursive. So I want to end there. If there are questions, ask questions. If not, you'll have a chance on Monday to ask more questions about static analysis. After Monday, so we will have still Wednesday and then the following Monday, and I'll talk about optimizations a little bit for those last two lectures. There's one final thing I want to say, and I posted it in Piazza already, but course evaluations are running starting today until the last day of classes, which is 2 weeks from now. So from today to 2 weeks from now, please go and complete a course evaluation. So they're online, and there's a link to them in Piazza. It's evaluate.uwaterloo.ca. Please do fill them out. And, especially I always go and read all the comments, obviously after the marks are submitted and everything. And I don't get to see your names, right? I only get the comments anonymized, but I always read the comments and try to use them to improve the course for future offerings. So that's really valuable. So please do fill them out. I also look at the sort of the multiple choice questions, but the multiple choice questions, they're the important people who look at them are like the university administrators and the dean and those kinds of people when they decide who gets to teach which course and when they're making those kinds of decisions. So please answer those honestly. But for me, the value is especially the written comments. If you can, give me constructive comments that are ways to make the course better for future students. Okay, so please fill those out when you get a chance. Any last questions or comments? Okay, so Monday, it's Easter Monday, but we do have a lecture on Monday. So have a good couple of days, have a good weekend, and I'll see you on Monday. Okay, bye.